So, good morning, all. Thank you for coming to these presentations. It's an honor to become a presenter for fourth Borobudur International Symposium 2022. First of all, let me introduce myself. My name is Ferdi Famgeorgy. You can call me Willy. I am come from Department of Mechanical Engineering, Faculty of Science and Technologies, Sanata University, Yogyakarta. And today I will show you about 3D Airlift pump simulation with variation of the nozzle diameter based on computational fluid dynamics. So in this presentation, will be divided into three main parts. The first part is introductions. The second part is talk about research method, and the last one is talk about result and conclusions. Let's begin from the introductions. So as we know that uh, fluid liquid fluid liquid or water has always flow from the place of higher pressure to the lower pressure, and to be able to drain water from a lower pressure to the place of higher pressure, we need a tool that called as pump. And one of the variation pump that I use in my study is the airlift pump. The way that airlift pump work is to inject air into the nozzle at the bottom of the pipe containing liquid fluid. In this case is water, which utilize the difference in buoyancy force and can lift the liquid fluid out of the top of the pipe. Airlift pumps are commonly used for underwater operations such as sample collections and mining, removing water from mines, pumping sand and water slurries, and transporting solid material mixtures. And airlift pump has some advantage like simple working principle, no physical contact with element of the mechanism of pump, and be able to lift liquid and solid mixture and solid fluid mixtures, and have a disadvantage points like small efficiency. So for problem formulation here, the airlift pump works on multi-phase flow, liquid and gas, based on the aeration phenomenon. The result of the phenomenon that occurs in the form of a flow patterns. And the larger the gas injected into the nozzle, the more random the flow pattern formed will be. And here, the performance of the airlift pump is affected by pipe height and diameters, nozzle diameter, and the last one is air injection systems. And variable that cause of flow pattern is by pressure drop and geometry constructions. And for the problem formulation here, as we know that the main component of the airlift pump is included by first nozzle that used as to inject compressed air in the form of mass flow rate of air to the bottom of the pipe. And the second one is a pipe. Pipe is used as cross sections of liquid fluid. And here I have a zone that I call as inner air chamber that use is a meeting and a mixing of two types of different liquids contain air from nozzle and water from the pipe. And for the limitation of the issue, research is focused only on the flow patterns that occur in change the diameter of the nozzle, and the research focus only on the flow pattern that occurs in the charge in the mass flow rate in the nozzle. And for the research objective here, to knowing the effect of variation in the size of the nozzle diameter on the fluid outlet discharge, and also knowing the phenomenon of flow pattern in the counter pressure and also from streamline velocity. Here, a research variable. There are two type of variable. The first one is free variables of nozzle diameters, include by 10 millimeters, 12 millimeters, 14 millimeters, and 16 millimeters. And also free variable of mass flow rate include by 0.010 kilogram second, 0.015 kilogram second, 0.020 kilogram second, 0.025 kilogram second, and 0.0230 kilogram seconds. And research variable of bound variables is airlift pump outlet flow discharge. And we continue to the research methods. So in this study, I used the ANSYS Fluent 19.2 application based on computational fluid dynamics or CFD. That is one of the branches of fluid dynamics using method and algorithm in computer. These two methods are used to solve and analyze problems in fluid flow. When using computational fluid dynamics or CFD, the computer will calculate millions of calculations to simulate the interaction between liquid, gases, and also liquid solid. And for simulation stage, they have three simulation stage. The first of all is pre-process, include drawing geometry of Airlift pump, meshing process, provision of boundary conditions, and the second one is solver, is about setup solution control, and then initialization process, and the last one is run calculation, and also the final stage is post-process, include charting, plot control pressure, and plot streamline velocity. And for design 3D design of Airlift pump here, as we know that Airlift pump have two main components, that is nozzle and pipe. And from the nozzle, I'm setting it as inlet air, and for pipe, I'm setting it from the bottom of the pipe as inlet water, and at the top of the pipe, I'm setting it as outlet fluid mixture. And here we got a geometry of Airlift pump here with height of the pipe is 37.5 centimeter, and the diameter of the pipe is 1 inch or 2 centimeter point 54, and have its variation of the nozzle diameter of 10 millimeters, 12 millimeters, 14 millimeters, and 16 millimeters. And this is a mesh generation or meshing. What is meshing? Meshing is process of dividing the regions into several cells. And in this simulation, I use hex dominance, which is had a dominant and have accuracy in calculation that are close to the real one. And for the meshing size, for nozzle, I'm setting it at 1 millimeter, and for pipe meshing size, I'm setting it at 1.5 millimeter. And we got here a detail of meshing Airlift pumps by using variation of diameter nozzles, 10 millimeters, 12 millimeters, 14 millimeters, and 16 millimeters. We got details of meshings such as number of cells, number of nodes, mesh type, and quality of mesh. And also, we continue to do research result and conclusions. Here, we got a mesh flow rate versus output discharge by using variation of diameter nozzle 10, 12, 14, and 16 millimeters. There is show a decrease in the discharge value with variation of the nozzle size that increasing bigger. And there's a difference phenomenon in 12 millimeter nozzle, which produce discharge value greater than 10 millimeters nozzles, starting at 0.020 kilogram per second mass flow rate until 0.030 kilogram per second. And in addition, we can assume that for a height of pipe 37.5 centimeter and 1 inch diameter of pipe, we can use nozzle 10 millimeters at mass flow rate 0.010 kilogram per second to have the best performance of Airlift pump in this case. And also the phenomenon of counterpressure here. What is counterpressure? What it for? So counterpressure here is used to show the value of the pressure range that occur in one time, and also can show the area that experience a drop pressure that has pressure range value ranging below the 0 kilopascal. And here, as an example, I use a mesh flow rate 0.020 kilogram per second with variation of diameter nozzle is 10 millimeters. We got a drop pressure here and the higher pressure here. For nozzle 10 millimeters, we got range pressure control from minus 921 kilopascal until 1338 kilopascal. And for nozzle 12 millimeter, we have range from minus 190 kilopascal until 721 kilopascal. And for the result of mass flow rate with the same mass flow rate of nozzle 14 millimeters, we got range from 1000 minus 1627 kilopascal until 1997 kilopascal, and for nozzle 16 millimeters, we got range pressure counter from minus 637 kilopascal until 1297 kilopascal. And for streamline velocity flow patterns phenomenon, what is a streamline velocity? What it for? So streamline velocity is used to show the shapes of the flow pattern created by velocity of the fluid flowing. And the more random the shape of streamline velocity flow pattern, the faster the velocity of the fluid flowing. And here with the mass flow rate 0.020 kg per second at the nozzle 10 millimeters, we got range from 208 until 2077 meter per second. And for nozzle 12 millimeter, we got range from 95 until 191 meter per second. And with the same mass flow rate 0.020 kilogram per second from nozzle 14 millimeters, we got range around 116 meter per second. And nozzle 16 millimeters, we got range for velocity streamline around 41 until 82 meter per second. And for the conclusion of this study, first one is in simulation test with variation in nozzle diameter of 10 millimeters, 12 millimeters, 14 millimeters, and 16 millimeters at mass flow rates of 0.10 kilogram per second until 0.30 kilogram per second, with variation of nozzle diameter size getting larger or bigger, will cause decrease in the discharge value of fluid outlets. And also the result obtained from each variation, each mass flow rate variations, and the increasing size variation in the diameter of the nozzle produce a random contour pressure shape in each variation with a variety of pressure. And also the form of the streamline velocity flow pattern obtained becomes regular with a decreasing range of velocity value. Okay, that's all presentation from me. Thank you.